So now let's put our newfound knowledge about how to find the integrals of absolute values of functions, as well as the relationship between distance, displacement, velocity, and speed, all to the test, shall we? So we're going to find a mass hanging from a spring. I guess we're not going to find it, it just is. A mass is hanging from a spring and it's set in motion, and its ensuing velocity in inches per second is given by v of t equals 2 pi cosine of pi t for t greater than or equal to 0 seconds. Assume that up implies positive and that the mass begins moving from the spring's natural resting position. Okay, so just so we all are clear, you have kind of a spring and you have a mass sitting right at the bottom of that spring. Okay? And so that mass is sitting there and it has a natural resting position. So this is the natural rest. Right? If you just aren't touching it and it's not bouncing, it's just going to stay there. And then it has a velocity equal to 2 pi cosine of pi t. So they gave us a couple pieces of information, and I don't want to let one of them go by. That natural rest right there is letting us know that it begins moving from there. So that means that s of 0, which is s sub 0, is 0. That's what they're telling us, that it begins from that natural resting position. So that'll be useful. And they also let us know that, and it makes sense, but up implies positive, which, not entirely surprising, but it's good to know that up is positive, right? So up is positive. Okay, first bit, we want to find the position function. All right, so to find the position function, s of t. Well, s of t, of course, is position, which is the integral of, I should make a little bit more note here, sorry. I got too excited for myself here. Okay, find position. Because just like in our worksheets or in our notes, we want to make sure that we're nice and organized here. All right, so position is by definition s of t for the Latin, right? Situs. So it means the situation. So I want to find the integral of velocity, which is the integral of 2 pi cosine of pi t dt. And this is why we reminded ourselves how to do u substitution, because that is a function nested inside another function. And therefore, u, I'll just put it over here, u is equal to pi t, and du would be equal to pi dt. That's the pi and that's the dt. So when I do my u substitution, it'd be the integral of 2 and then cosine of u du. And those two letters du take care of the pi and the dt for me. All right. Well, the integral of cosine is sine. So this is 2 sine of u plus an arbitrary constant, right? Some constant unknown. And that would be 2 sine, well, it's not unknown. We're about to write it in a second. 2 sine of pi t, because that's what u was, plus c. Now, we're going to find that c. So this is a general solution, if you remember learning that in Calc 1. This is called a general solution. It's general because c is in there. Now, it's tempting to say, oh, well, c must be 0, right? Yes and no. With the transcendental functions especially, we have to be more careful than that. So we have to use s0 to find c. And that's not a step you can skip. In polynomials, it's really easy, but in transcendental functions like sine and cosine and logarithm and things like that, you have to go find it. So 2 pi, oh my goodness, 2 pi, 2 sine, my goodness, 2 sine of pi times 0 plus c is equal to 0. Okay, well, pi times 0 is 0, and the sign of 0 is 0. So this whole thing is 0. So 0 plus c is equal to 0, and that means that c is equal to 0 also. Now, it's tempting, I know, to skip over this, but do not. You have to do this with transcendental functions. Let me make this. And actually, not even just transcendental functions. I mean, rational functions, all sorts of stuff. Basically, non-polynomials. Let me put it that way. With non-polynomials, do not skip that step. You just can't. So with non-polynomial, you just have to go find it, right, if you can. So do that work. Make a little note to yourself, right? Do not skip it, right? Find it. All right, so we found that C0 is equal to 0 also. Great. So that means that the particular solution, so this was the general solution up here, but now we know because C is equal to 0, that means that the particular solution, the special solution, would be S of t is equal to 2 sine of pi t. That is the position function. Yay, part A is done. Part B, they would like us to graph it. And this is why I have Desmos. Yes? Okay, so I'm going to graph this bad boy in Desmos. And then I'll try to cobble it together on my paper. But there it is. So 2 pi sine of pi. I did x instead of t. No particular reason. It usually works a little bit easier in Desmos if you use x. All right, so I'm going to draw that on a sheet of paper. 1 second. You'll notice that it has a peak at 0.5, and then an intersection or a 0 at 1, another 0 at 2, another 0 at 3, and at 4, and so on. And it reaches a height of 2 and a trough or a valley of -2. Okay, so I've drawn that on my paper as best I am able. I'm not the best drawer in the world, but of course I gave it scale, right? I could give it 1, 2, 3 right there, and so be it. Okay, now the real interesting parts. So this was not too bad. We already knew how to do this. We know how to use substitution. How much distance has the mass traveled in those 4 seconds? Okay, so this is the position function. But remember, position is not how we find distance. Distance is the integral of the absolute value of velocity. Velocity, of course, was given to us in the problem. So velocity is, let me draw you a little picture. It was 2 pi cosine of pi t. So let me just graph that really quickly with Desmos. You can see the difference. So that's position, that's velocity. See it? So it goes up to about 6.28, say 2 pi. So it's 2 pi, -2 pi, and so on. And it's also hitting 0 and 4. So I'm going to quickly sketch that. All right, not the best graph ever, but I just wanted to kind of get us to note this. So this is positive, this is negative, this is positive, negative, and positive. And again, I'm not the best drawer in the world, but they're supposed to be equal. I think my middle line is actually kind of in the wrong spot. Let me see if I can fix it really quickly. There we go, that's a little better. I should have probably drawn the curve first instead of the line. Okay, so you can see that the displacement, you have 2 full troughs or valleys and one big full hill here and a half hill and a half hill. So the displacement would actually be from 0 to 4 of velocity. It would actually be 0. You can tell just by looking at the graph. The negatives and the positive parts will cancel each other out, and you'll end up with a 0 for displacement, which luckily for us was not actually what I asked us to graph, but there you have it, right? So the negatives and the positives all cancel. good to us. Okay, so what we really want is the distance. Okay, well, distance is the positive, and then you turn the negative parts positive. So this valley that used to be down there for displacement, this green part down here, gets flipped over and turned positive. So you make every little piece of it positive. Okay, well, if you're thinking, how am I going to do that as an integral? Good question. All right, but first, before I get into that, let me draw that picture, or do my best to. 1 second. All right, that is speed, right? Now, I don't want to find all of that. That's because I'd have to do all of these. I mean, this is 4. This is 2 right here. That's 2.5, 3.5. That's 3. It'd be a mess as an integral. I'd have to do so many different integrals. So the easier way to do this is to not find all the integrals, to only find the part of it that you need. So what you do is you find this little bit right here, which is the equivalent to half of one of these hills. And then you just count. I have 1/2, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So to find the distance, I'm going to be clever about this, which is the integral from 0 to 4 of the absolute value of the velocity. But I don't want to break it up into that many integrals. So I'm going to make it 8 times the integral from, well, this is 1 right here, so that has to be 0.5 right there. So I'm going to go from 0 to 0.5 of the velocity function, which was 2 pi cosine of pi t dt. Right, I'm doing this based on symmetry. Right, way easier to do it that way than to try to do this all by hand. What a mess. Okay, so this would be equal to 8. The integral of cosine, we actually already did this on the previous page, right? It's 2 times the sine of pi t. We're going to take that from 0 to 0.5. Sine of 0 is 0, so that doesn't really make any difference. So it's 16 times the sine of 0.5 pi, which is pi over 2. Right? When the sine of pi over 2 is 1, so that would be 16 inches. Because this right here is 1. Yay! Wonderful. That wasn't so bad. It could have been a lot worse. All right, so that wasn't too terrible. The trick is using that symmetry. That's nice, right? Use your head. Nobody wants you to do 9 different integrals. That's just terrible, right? If there's symmetry to the graph, then use it. Okay, last but not least, at what time does it reach its low point? In those 4 seconds, the mass reaches low point. Okay, so low point would mean you have a local min on the position function, right? Okay. Well, where does that happen? Well, we learn in Calc 1 that local minimums happen when your derivative, which in this case is velocity, is equal to 0. Okay, so where does that happen? Well, the velocity function is 2 pi cosine of pi t, and that is going to be equal to 0. So the question is, what angles would that be true for? Now keep in mind, this is an angle, some angle of some kind. Now, what angles would that be true for, right? Because basically it means the cosine is going to be 0, because the 2 pi has nothing to do with it. So what angles on a unit circle, oh, I should have drawn the circle first before I drew the grid. Sorry about that. What angles have cosine equal to 0? Where's the cosine 0? Well, it's 0 here and it's 0 here, at the top of the circle and the bottom of the circle. Okay, so those values would be, let's think, pi over 2 and 3 pi over 2 down at the bottom. And then, let's see, 5 pi over 2 and 7 pi over 2. and 9 pi over 2, and 11 pi over 2. We're getting the idea. Okay, so that angle which is pi t, because you're actually trying to solve for t, but so pi t, that angle, yeah, let me write it this way. That angle, which is pi t, is equal to these values. Let me just write them down. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, and I'll put in the other ones as well. And I'll just put a dot, dot, dot at the end of it because we all know it keeps going and going and going forevermore. Gotta love trigonometry. Okay, well, I don't want pi t, I want t. So t by itself, what I would do is multiply this whole thing, because this is an equation. So I multiply by 1 over pi, right? 1 over pi will make the pi over here cancel. So pi over 2 times 1 over pi, it'll cancel out the pi's and just leave you 1/2. And then 3 halves, and then 5 halves, and then 7 halves, and then 9 halves. And then we can be done right there. And the reason we can be done, comma, comma, comma. We can stop because 11 over 2 is 5.5, right? That's too big. Remember, we're only allowed to look from 0 to 4 is our domain. Right? 9 over 2 is also too big. That's 4.5. So both of those are too large. They're outside of the domain. And so we can cut them off and kick them out. So that means that the local minimums happen at these 4 values. Or do they? Well, local critical points happen at these 2 values, but we need to know if they're minimums or maximums. And the easiest way to do that is to take the second derivative. S double prime, the second derivative of t, is equal to, well, let's see, if that's S prime of t, then S double prime would be negative 2 pi squared times the sine of pi t. And so I need to know if, actually, let me put that up here. I'm just going to say note. S double prime of t is equal to negative 2 pi squared sine of pi t. Why am I doing this? Well, I need to know which ones of these are positive and which one of these are negative for the second derivative test, right? So I'm using the second derivative test. Do you remember Calc 1? Second derivative test. Derivative. Okay, so S prime or S double prime here is, well, let's go check. I mean, this is what Desmos is for, right? Okay, so I go grab, whoop, wrong thing, sorry. There it is, Desmos. So if I grab my second derivative test right here, I can tell it, hey, here are values, right? A half, 3 halves, 5 halves, 7 halves. Tell me what the S double prime is at those specific values. And it's telling me it's negative, it's positive, it's negative, it's positive, right? So I can write that down. Negative, positive, negative, positive. All right. Oop, sorry about that. Okay, so my second derivative is negative here, positive here, negative here, positive here. Negative means it was concave down, so it's a max. Positive means it was concave up, so it's a min. Negative means concave down, so it's a max. Positive means concave up, so it's a min. Remember the second derivative test from Calc 1? All right, therefore, we know that 3 halves, this one right here, and this one right here are what we wanted. They were the mins on this. Or when the mass reaches its low point. can even make a note to myself that I used Desmos to help me out.